Specifically, he points to the unresolved mystery of quantum mechanics, the measurement problem. In the quantum world, particles can exist in multiple states at once. A superposition. This blurry state of potential persists until a measurement is made, at which point the system collapses into one single definite reality. Mainstream interpretations have struggled to explain what constitutes a measurement. Penrose suggests that it is not an external observer, but gravity itself that resolves this ambiguity. He posits that every superposition has a tiny amount of mass energy associated with it, creating a minuscule warp in spacetime. When this warp reaches a certain threshold, it becomes unstable and collapses on its own. This process, called objective reduction, or OR, is a proposed physical law, not just an interpretation. It suggests that reality is constantly choosing its state based on a gravitational trigger. The theory, developed with anesthesiologist Stuart Hameroff, is called orchestrated objective reduction, or ORCH-OR. It hypothesizes that this gravity-induced collapse is not random noise but is orchestrated within the brain, specifically inside tiny protein structures within our neurons called microtubules. These microtubules, the theory claims, can sustain quantum superpositions long enough for them to reach the gravitational collapse threshold. Each moment of orchestrated collapse, according to ORCH-OR, corresponds to a moment of conscious experience. Here, then, is the line in the sand. On one side, we have the computational theories, GNW and IIT, which state that consciousness is a pattern of information flow, independent of the physical substrate. On the other side, we have ORCH-OR, which claims consciousness is a specific, non-computable physical process intimately linked to quantum gravity, occurring within a unique biological structure. This is not just a philosophical disagreement. It is a clash of two fundamentally different views of the universe and our place within it. For the first time, this clash presents us with a possibility that was once unthinkable, a clean, falsifiable experiment. A test that could distinguish gravity from code and finally begin to answer the most profound question we can ask. Before we venture into the exotic world of quantum gravity, we must first understand the reigning paradigm, the powerful and elegant idea that consciousness is, at its core, a product of computation. This viewpoint begins with a simple, yet profound observation. The brain is an information processing machine. It takes in sensory data, recognizes patterns, accesses memories, and generates outputs in the form of thoughts, emotions, and behaviors. In this framework, the mind is what the brain, the intricate dance of 86 billion neurons firing in complex sequences, is seen as a form of biological computation, different in its wet substrate, but not fundamentally different in its logical principles from the silicon chips inside your smartphone or a data center's vast server racks. This computational view is deeply rooted in the scientific materialism that has successfully explained so much of our world. It treats the brain as a physical system governed by the known laws of chemistry and electricity. There's no need for mysterious, non-physical forces or souls to explain the mind. Instead, consciousness is considered an emergent property. Much like the intricate patterns of a flock of birds emerge from the simple rules followed by each individual bird. No single neuron is conscious, just as no single bird understands the concept of a murmuration. But when you put enough of them together, connected in just the right way, a new, higher-level phenomenon, conscious awareness, is believed to simply switch on. The core appeal of this perspective is its straightforward, mechanistic nature. It suggests that if we can fully map the brain's connectomy, the complete wiring diagram of all its neural connections, and understand the rules of its signal processing, we can replicate it. Consciousness, in this model, is substrate independent. It doesn't matter if the logic gates are made of proteins and lipids or silicon and copper. As long as the computational architecture is the same, the resulting experience should be the same. This is the foundational belief that drives much of modern artificial intelligence research. that building a truly conscious machine is not a question of, but of our processing power and architectural understanding becomes sufficiently advanced. Therefore, the central task for a computational theory of consciousness is to identify which specific type of computation or information architecture gives rise to subjective experience. What is the special algorithm that our brain is running? The search for this consciousness code has led to several sophisticated and compelling theories. They don't seek new laws of physics. Instead, they look closely at the brain's known structure and function, attempting to pinpoint the precise data handling trick that separates the lights-on awareness of a waking mind from the dark, silent processing of a computer running its background tasks. These theories provide the essential baseline against which any alternative like Penrose's gravity-based model must compete. One of the most prominent computational theories is the Global Neuronal Workspace, or GNW. So imagine your brain as a massive organization full of specialized departments. There's a visual department, an auditory department, a memory archive, a language center, and, a planning committee. Most of the time, these departments work locally, processing their own data without bothering the rest of the organization. This is what we call unconscious processing. For example, you can walk down the street while your motor cortex handles the complex mechanics of balance and gait, all without your conscious involvement. But what happens when something truly important occurs, like a car horn blaring or someone calling your name? That specific piece of information needs to be shared with everyone. GNW proposes that consciousness is what happens when information goes viral within the brain. A piece of sensory data, or maybe an internal thought, gains access to a central broadcasting system, a global workspace, composed of a network of long-range neurons, primarily in the prefrontal and parietal cortices. Once information enters this workspace, it is broadcast widely across the entire brain, becoming available to all the specialized departments. Your language center can now report on it. I hear a horn. Your memory department can search for context. That sounds close. And your planning committee can generate a response. I should jump back onto the sidewalk. According to GNW, this state of global information availability consciousness. This model makes clear, testable predictions. Neuroscientists can look for signatures of this global ignition. When a person becomes aware of a visual stimulus they were previously ignoring, we should see a sudden coordinated burst of activity across this widespread brain network. And that is precisely what brain imaging techniques like EEG and fMRI have shown.